Next problem I want to work on is chapter 19, number 2, is to show that Q adjoin square root of 2 and square root of 3 equals Q adjoin square root of 2 plus square root of 3. That's kind of a weird thing to think about. What does it imply? What does the truth of this imply? This is evidently true because the book says show it. Take them one at a time. Think of this as the smallest subfield of, again, either the complex numbers or the reals. I can do the reals in this case because square root of 2 and square root of 3 are real numbers. Though, again, it's sort of safer in general to think of the large field as being the complex numbers. The smallest subfield of the complex numbers containing all the rationals, also containing square root of 2, also containing square root of 3. And plenty more numbers that are not mentioned here. Plenty more new numbers that are not rational. They would all be real numbers. They couldn't be non-real numbers, like I is not going to be in there. But there are plenty of other numbers. For example, square root of 2 cubed, 2 times square root of 2, for example. 1 over square root of 2 as well would be another example, which is the same as square root of 2 over 2, etc. Things like that. This is the smallest subfield of the complex numbers containing all the rationals and containing this sum square root of 2 plus square root of 3. By definition. The claim is these sets, these fields are equal. How do you prove that? One step at a time. You try to prove they're equal as sets. The argument, however, for why one's a subset of the other and vice versa, it's kind of subtle. Okay. One of the inclusions is definitely easier than the other. And I always have to think carefully about which inclusion is definitely easier. I think it's this inclusion that's the easy one. Yeah. Why? Okay. Again, by definition, let's go ahead and write it out. By definition, Q adjoin root 2, root 3 is the smallest subfield. Again, I could write R, but I'll write C in general to play it safe. Of C containing all the rationals and square root of 2 and square root of 3. Since it is a subfield of the complex numbers and the real numbers, it is a field. So by definition of being a field, it's got to be closed under addition, closed under subtraction, closed under multiplication, closed under division of not dividing by 0, because division is multiplying by the reciprocal, the multiplicative inverse. So in particular, it's got to contain the sum of these two things, square root of 2 plus square root of 3. Since this thing is a field by definition, you don't have to prove that, it's closed under addition. So square root of 2 plus square root of 3 is an element in there. I claim this is enough to prove this inclusion. Why? Because by definition, this thing on the right is the smallest subfield of C containing all the rationals and containing square root of 2 plus square root of 3. But this one contains it as well. So it's got to be possibly bigger. Certainly not smaller, because that's the smallest one. Let's write it out. Since this thing is the smallest subfield of C containing all the rationals and square root of 2 plus square root of 3. Emphasis on the word smallest. We must have, it must be the case that this thing is possibly bigger, so we have this included. Okay, that's the easy direction. Yikes. The other inclusion, the other direction is harder. Show this is a subfield of that. A subset, say. We are still going to use the definitions of this thing here as being the smallest subfield of C containing all the rationals and containing square root of 2 and square root of 3. We're going to try to use that fact by showing that this thing on the right contains both square root of 2 and square root of 3. But how? Just because it contains square root of 2 plus square root of 3, a priori at least, is seemingly not enough to show it contains square root of 2 and square root of 3 individually. Because closure says if you've got two elements and you add them, then the sum is in the set. It doesn't work the other way around necessarily. If the sum's in the set, the elements aren't necessarily in the set. For example, 1 plus 3 is an even number, but neither 1 nor 3 is even. For example. So, how do we do this? It's a bit of trickery. It's a bit of experimentation. So we're gonna do some scratch work here. Somebody eventually just figured this out by doing some scratch work. What kind of scratch work did they do? Eventually somebody came across, I wonder what happens if I do this. What would happen if I simplify that thing? Can I simplify this thing? Well, first of all, before I simplify it, I should note that this is an element of Q adjoining square root of 2 plus square root of 3. Why? Because it's got to be because it's closed under taking inverses. 1 over this element has got to be in here because it's a field. It's the multiplicative inverse. Let's rewrite it again and do a common trick in this kind of circumstance. Let's try to maybe rationalize the denominator. How? By doing this multiplication. If I do it to the bottom, I got to do it to the top as well. You've done this kind of thing before. Long in your past, 8th, 9th, 10th grade, something like that, right? Rationalizing the denominator. It's a little weird because I've got a sum in the denominator instead of just an individual thing. But if you multiply by this trick of multiplying with a minus sign there, on the bottom, probably the square roots go away because of foiling and the outside and inside terms canceling. I have to, if I multiply it on the bottom, I got to multiply on the top as well, so that I'm really multiplying by 1 and not changing the value of the number. On the top, you still have square roots. On the bottom, what happens when you FOIL? First times first, square root of 2 times itself is 2. Outside times outside is minus square root of 2 square root of 3. Inside times inside is plus square root of 2 square root of 3. And last times last is minus square root of 3 squared minus 3. These things cancel. 2 minus 3 is negative 1. This simplifies to square root of 3 minus square root of 2. Weird. Is that really right? Is square root of 3 minus square root of 2 really the multiplicative inverse of square root of 2 plus square root of 3? That seems really weird. Let's try with the calculator here to check it, see if it seems right. Square root of 2 plus square root of 3 is about, well, close to pi. How about that? Not equal to pi, but close. 3.14626. What's its multiplicative inverse? It's about 0.3178. What's square root of 3 minus square root of 2? How about that? It works. Very unexpected, right? This is right. You could also multiply. Let's go ahead and multiply to check it. FOIL that out. Square root of 2 times square root of 3, which is, by the way, square root of 6 as well. Then multiply those two, get minus 2. Multiply these two, get plus 3. Multiply those two, get minus square root of 2, square root of 3. Cancel, cancel, 1. It's a way to check it. To really prove it. The calculator was really not a proof, right? Just an indication that it seems to be right. All right, is this helpful? We know this is in here because this is a field and square root of 2 plus square root of 3 is in there. So it's multiplicative inverse is in there. But that multiplicative inverse is this. Therefore, this is in. Therefore, that's in this field because it equals this thing, which is in the field. And so what? If I take this thing and add this thing, I'll get a field element. Or if I take this thing and subtract that thing, I'll get a field element because of closure. Therefore, square root of 3 minus square root of 2 plus square root of 2 plus square root of 3 is in the field by closure under addition. But what does that simplify to? The square root of 2's cancel. This is none other than 2 square root of 3. So 2 square root of 3 is in the field. Divide by half. Therefore, square root of 3 is in the field. Likewise, if I had subtracted instead of added, I'd done maybe square root of 2 plus square root of 3 minus square root of 3 minus square root of 2. The square root of 3's cancel. This is 2 square root of 2. That's got to be in this field. Divide by 2. And I can say, therefore, square root of 2 is in the field. This is all scratch work so far. Okay. Help me problem solve to do what I was hoping to do, what I said I wanted to do at the beginning. The goal again was to show that this inclusion is true, which means the goal was to show the thing on the left is a subfield of the thing on the right. How? I'm not going to write it all out, but I'll just verbalize it. That's the smallest subfield of C containing all the rationals, also square root of 2, also square root of 3. If we can show this contains square root of 2 and square root of 3 individually, we'd be done. Definitely contains all the rationals. That's the smallest one. If this contains it, it's got to be possibly bigger, certainly not smaller. I have put this on test at the final exams before, this kind of problem. Probably not the entire proof, but maybe part of it, and maybe the harder part where I tell you, I think what I've done in the past is I've told you the scratch work to use, because, you know, realizing this is the kind of scratch work to do to figure it out is, you know, too anxiety producing during an exam, I think. It's unclear that it's going to work, but it does. What would this imply about the degrees of these extensions of Q? Let's think about this thing here. We could make a diagram. It's called a tower of fields. Put Q on the bottom. Put Q adjoin square root of 2 above Q. Maybe make a line. This is kind of like a lattice. We made subgroup lattices before, subring lattices before. This is a subfield lattice, you could call it, but it's usually called a tower of fields. I guess this thing would be the same as this. Yeah, effectively by definition, if I adjoin square root of 3 to this field, that really is the same as adjoining both square root of 2 and square root of 3 to Q itself. Definitely we have inclusions going up here. That's a subfield of this, and this is a subfield of that. This one in the middle, for example, does not contain square root of 3. We might wonder, what are the degrees of these extensions? In other words, what's the dimension of this field as a vector space over this subfield? And what's the dimension of this thing as a vector space over this subfield? This is done in chapter 20. How do you figure out that degree? You can do what we did with the previous example. Take this example here. You could find an irreducible polynomial over Q that square root of 2 is a root of. A minimal degree one, actually, you'd like. And if you can find such a minimal irreducible polynomial, its degree will be the degree of this extension. What polynomial would it be? How about f of x equals x squared minus 2? As an element of Qx, it is irreducible. You can apply Eisenstein's criterion. It also definitely only has 2 roots that are plus or minus root 2 that are not rational numbers. You can't factor it as a product of linear polynomials over the rationals. It's degree 2. It's irreducible. It's going to turn out the dimension of this as a vector space over that is going to be 2. The degree of this 2. I could use this notation again. What about the dimension of this one? Can I find an irreducible polynomial with coefficients from this field in which square root of 3 is a root of it? Yes, f of x equals x squared minus 3, thought of as an element of not q of x, but q adjoin root 2x. Does turn out to be irreducible over q adjoin root 2. Eisenstein's criterion would not be allowed to be used, though, because Eisenstein's criterion is only for irreducibility over q. However, it's still not too hard to argue it's irreducible over q adjoin root 2 because you can't factor this as a product of linear polynomials over this field because square root of 3 is not in that field, and neither is negative square root of 3. That's degree 2. It's irreducible over q adjoin root 2. This extension has degree 2 as well. Save space and time. I'll just use arrows there. The overall extension has degree 2 times 2, it turns out. 4. That's a theorem in chapter 20. In other words, this is a 4-dimensional vector space over this. Could I find a basis for this over this? Yeah. What you do is you take the basis for this over this and the basis for this over this and find all products of elements. Let's write it out here. 1 comma square root of 2 is a basis for q adjoin root 2 over q. Also, 1 adjoin root 3, it turns out, is a basis for q adjoin root 2 comma root 3 over q adjoin root 2. It turns out if you look at the proof of the theorem that this is all referring to, that if you form all products of the numbers in these bases, 1 times 1 is 1, square root of 2 times 1 is square root of 2, square root of 3 times 1 is square root of 3, and square root of 2 times square root of 3 can be written as square root of 6. That is the same as square root of 2 times square root of 3. That is a basis. Just out of room here for the biggest field here, q adjoin root 2 comma root 3 over the smallest field, q. And it's got 4 elements. It's a degree 4 extension. these extensions are algebraic as well. In fact, there's a theorem that says if your extension is finite, it's algebraic. If the degree of the extension, the dimension of the bigger field as a vector space over the smaller field is finite, then the extension is actually algebraic, no transcendental numbers in it.